Good morning, everyone. I'm Zhang Yihong from National University of Singapore. So today I will present our work about Bayesian optimization with binary auxiliary information. So this work is collaborated with Zhong Xiang, who is my lab mate, and Prof. Brian Low. So first, I will give a brief introduction of the background of BO and also the motivation of our work. So Bayesian optimization is a sequential design strategy for global optimization of some black box functions. So usually for these black box functions, they are non-convex and we cannot have the derivative of them, and also they are usually very expensive to evaluate. And a very popular application of BO is the hyperparameter tuning problem of the machine learning models. So in this application, usually we treat the hyperparameters as the input and the performance of this machine learning model as the output. And we treat the whole machine learning model as a black box function. And other BO applications include like to optimize the policy or configuration of the robotics, and it has also been used to optimize the web design or optimize the formulation and the process parameters of the new product development. This is general steps for the conventional BO algorithm. So in each BO iteration, we will first select an input X and then evaluate the black box function at this input to get an observation. Then, given existing observations, we build a surrogate model and using the result of this model to construct some acquisition functions. Then this acquisition function is used to select the next point that we want to observe. However, the conventional BO algorithm is still quite expensive because in the BO applications, these black box functions are always very expensive to be evaluated. Therefore, in the past few years, many works have been focusing on how to speed up the BO process. One class of them is known as the multi-fidelity BO. So in these works, they try to leveraging some low-cost, low-fidelity auxiliary functions to improve the optimization of this expensive target function. And in all these works, they assume that the target and the auxiliary outputs are continuous. So here, our question is, are all the low-cost information continuous? Then the answer is no. There actually exists other types of low-cost information. So in our work, we will focus on the binary ones, which can be observed in different real-world applications. For example, when we use Bayesian optimization to find the optimal policy, the target may be to maximize the success rate averaged over multiple environments. Then if we consider only one single environment, the result of this task is success or failure, which is binary. Another example is in the hyperparameter tuning applications. Then here the target output is the validation accuracy when the training is finished. However, if we ask the question like whether the validation accuracy of this model will exist some specific threshold, for example 0.5, we may get a quite certain answer after only a few training epochs, and the answer yes or no is binary. The other example is the BO application that need to interact with the humans. So in these applications, ask the binary opinions, for example, whether you like this design or not, is usually much easier and faster than asking for the explicit rating from them. So in all these applications, we can see that the binary information is very cheap to be observed, and they all have some correlations with the target that we want to optimize. So in this work, we try to exploit this low-cost binary information to speed up the build process. So we call this mixed type BO because we have both continuous and binary outputs in the observations. In our problem, there is always one target objective function which returns the continuous output, and multiple auxiliary functions which return the binary output. And we assume that the target function is more expensive to evaluate than the auxiliary. The objective here is we want to select the most informative observations from the target and auxiliary functions, which have different output types for finding the global target maximizer. So to achieve this, there are some issues that we need to resolve. The first one is about the surrogate model. So when we design the surrogate model for mixed type BO, we need to consider how to model the cross correlations between the continuous and binary output. And also, for the auxiliary function, we need to consider how to deal with this non-Gaussian likelihood of them. Then the other issues is about the acquisition function. Because in the mixed type BO, the acquisition function will be used to select which input and which function we will evaluate in the next step. So for the acquisition function, it should be able to measure the contribution of the binary output for finding the target maximizer X star. And also to decide which function to evaluate, this acquisition function should be able to compare the contributions of the target of the continuous and the binary outputs. So next, I will give some idea about how we resolve this issue in our work. First, for the surrogate model, to model the cross-correlation between the continuous and binary outputs, we exploit the idea from the convolutional multi-output Gaussian process. So here, we assume that each n-node target and auxiliary function is defined as a convolution between a smoothing kernel and a latent function. Here, they have shown that if we assume the latent function is a Gaussian process and the kernel is Gaussian, then a joint distribution over the target and auxiliary functions will also be a Gaussian process. Then to generalize this convolutional MOGP to the mixed type outputs, we approximate the non-Gaussian likelihood for the auxiliary function as a Gaussian using the expectation propagation method. After doing this, given a set of observations with both continuous and binary outputs, the mixed type MOGP model can give an analytic predicted distribution at any input point for both the target and the auxiliary outputs. So this is an example about the result of the normal GP and the mixed type MOGP. Here, the observation is collected from a pair of synthetic target and auxiliary functions, which is shown in the figures A and B. And by comparing the results in figures C and D, we can see that by exploiting additional binary auxiliary observations, which is shown as the white color marker in the figure D, the mixed type multi-output GP can actually predict more accurate target function than the normal GP. Okay, then the next step is to find a acquisition function for the mixed type BO. So to answer these two questions, we define a distribution over the target maximizer. So here are three examples of the belief of this target maximizer. We can see that from the left to the right, the samplings of the target maximizer becomes more and more concentrated, and also more accurate. So intuitively, if we want to find a more accurate target maximizer, we can consider to reduce the uncertainty of the distribution. So then we can write the optimization function like this, which is called the mixed type entropy search. So here, this acquisition function will compute the information gain of the target maximizer from the next observation. And the observation can be either continuous or binary. As you can see, that it's quite similar to the entropy search for the conventional BO, and the only difference is that for the given part, the outputs for the observation can be both continuous and binary. And the problem for using this directly in the mixed type BO is that this entropy search acquisition function is not tractable and is very expensive to approximate it. Then to resolve this issue, we exploit the symmetric property of the conditional mutual information and convert it to its equivalent formulation, which is called the mixed type predictive entropy search. So here, this new formulation is the information gain of the next observation from the target maximizer. Then an interesting observation is that here, if we observe each of the entropy term separately, we can see that for the continuous output, it's a differential entropy. For the binary output, it's actually a Shannon entropy, and they are clearly not comparable. But if we consider the difference between these two entropies, it will be equivalent to the information gain of the target maximizer. So actually, the information gain is comparable between the continuous and the binary outputs. So given this observation, we can jointly optimize this acquisition function over both x and I to decide which input and which function to observe in each BO iteration. Next, this is the steps that we do to do an approximation for the mixed type predictive entropy search. So I'll just give the idea of it. First, we have proposed some mixed type random features method to sample the from the distribution of the X star for approximating the expectation. Then we propose some new constraints and select variables for the binary auxiliary output. Then approximate these constraints using EP. So I will not give the detailed information about it because of the time issue. Then I would like to show some experimental results for this work. So here, we evaluate the performance of different algorithms using the target function value at the recommended target maximizer, which is defined as the maximizer of the predictive mean function. So we compare the proposed algorithm with the conventional PES, which didn't utilize any binary auxiliary information. And also we compare it with the multi-fidelity GPU-CB, which use the continuous low-fidelity information. The first experiment is done for hyperparameter tuning of the CNN model with the Stephenson data set. Here we have 6 hyperparameters, and the target output is the validation accuracy evaluated by training the CNN using all the training data. Then for the auxiliary function, we construct the binary output by using the early stop decision. So to be more specific, we train the CNN model using 20% of the training data, and then apply the Bayesian optimal stopping after 20 training epochs. So for the BOS, it will try to estimate a probability that whether the final validation accuracy will exist some threshold or not when the training finished. The threshold is set at 0.5 in our experiment. Then if the BOS think that the probability is high enough, it will stop the training and return 1 or -1 according to its result. And otherwise, it will select to train one more epochs. A second experiment is to do the linear policy search for the couple task. Here we have 8 parameters, and the target function is the success rate average over 100 epochs, 100 episodes, and the auxiliary function is the reward of only 1 episode with a fixed starting point. So here is the experimental results. We can observe that for both the mixed type BO algorithm, they converge faster than they converge faster to a higher function value than the single PS. And also the mixed type PS converges faster than the mixed type ES because it has faster and better approximations. Then the mixed type BO algorithm outperforms the multi-fidelity GPU-CP in the CNN application, because when we do early stopping to collect the binary outputs, we can early stop the training in a very early stage, and it incurs much less time than evaluating the true validation accuracy. Okay, in the end, I would like to summarize 2 take-home messages. The first one is the low-cost binary information exists in many applications, and we can actually exploit them to boost the BO performance. And the second one is, if your outputs is from is in different types, like the binary and a continuous, and you want to measure and compare their contributions for finding the global target maximizer or some other variable, actually the information-based acquisition function is a very good choice. Thank you.